This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
I'm David Spergel. I'm a theoretical astrophysicist and a faculty member at Princeton. I'm succeeding Charlie as the next chair of the Space Studies Board. And I thought I'd begin, rather than tell a story about Charlie from 1964, move forward in time and tell one from 2014. Because I think it just captures a bit of the things that Charlie's been doing now. So last time I spent a lot of time with Charlie was in Beijing. Charlie had just flown in from Rome, where he was at a pontifical meeting on sustainability, meeting with the Pope. And we were in Beijing for a joint National Academy of Sciences, Chinese Academy of Sciences meeting on space science. And as many of you know, the Congress has basically forbidden NASA from saying the word China, let alone meeting with anyone from China. And Charlie felt that one of the things we could do as a National Academy is to have scientist-to-scientist connections, particularly among younger people. And I was there as one of the old guys. There was I had actually gone to the Soviet Union in 1988 for a similar meeting and was then in the young group. But with time, the Soviet Union falls, and I moved to the old group. And, so, it was just wonderful spending time with Charlie, and you really got the sense of this tremendous excitement in science. Charlie sat there, and there were speakers, young Chinese and young American space scientists in both heliophysics and astrophysics, and he was working very hard to stimulate conversation, make those connections. But what I remember most is sitting around after the talks were done over dinner, and about half a dozen people, maybe a bit more, stayed, probably about 10 of us around the table, 8 young scientists, Charlie and me. And we were just drinking and telling stories, and they were developing the kinds of connections we want. And I was impressed to see that, and I was also impressed to see Charlie, after flying on the red-eye from meeting with the Pope, was still able to stay up and drink with the youngsters. So when we celebrate the 100th birthday, we hope you're still drinking with the youngsters. I thought I would take advantage of being the moderator and just say a few things about the state of cosmology. And in many ways, it's a real contrast, I think, with, at least on the largest scales, with some of the stories we've heard about and we're thinking about plasmas, because the universe on the largest scales is really simple. And linear theory seems to describe everything that's going on. And while it's simple, it's very strange. And a lot of what we've learned about the larger scales will come from things like observations of the microwave background. This image shows the data from the Planck satellite, a European mission that has mapped the sky at high resolution, recently reported results, and report some more results in November. And what you're seeing here are tiny fluctuations at the part in 10 to the 4 level, part in 10 to the 5 level, in the temperature of the microwave background. We're looking back and seeing what the physical conditions were in the universe about 380,000 years after the Big Bang. And what we've learned from this and our observations of large-scale structure is that the universe is remarkably simple. It could basically be described by 5 numbers: how much matter there is in the universe, how many atoms there are in the universe, how old the universe is, how lumpy the universe is, and how that lumpiness varies with scale. All the fluctuations you see in that map are nearly scale invariant Gaussian random phase fluctuations. Their statistical properties can be characterized by two numbers, the amplitude and how it varies with scale. And the composition of the universe is in some ways very simple. In other ways, strange in that we've learned that plasmas don't make up 99% of the universe. They do make up 99% of the composition of the atoms, of ordinary matter, but that ordinary matter makes up only about 4% of the universe. And the rest is in the form of what we call dark matter, stuff that clusters on gravitational scales of galaxies, does not interact very much at all with ordinary matter. And even stranger, what we call dark energy, something that doesn't even cluster at all, doesn't respond to gravity. Our best idea is it's as energy associated with empty space. And one way we can get a picture of all this fitting is these are measurements of the microwave background fluctuations, where we took the map you saw and expressed it in spherical harmonics, looked at the amplitude of the spherical harmonics. The points shown here in blue are from the WMAP satellite, of which I was part. The green points from the ACT telescope in Chile, the red from the SPT experiment in the South Pole. And I should go back. And then the Planck results flash on, but I didn't make it cycle. And Planck is measured even higher resolution, got very consistent numbers. And what you see is the curve, which is the theory curve, goes through the points very nicely. Even more remarkably, we can take the baby pictures, and these are pictures of 3 randomly selected babies, all about 2 days old. And you run them forward in time, and if you know the initial conditions, you can predict the outcome. Now, those of you with children know that this doesn't work with children, but it does actually work on the largest scales with observations of large-scale structure. What we can do is take measurements of the microwave background, measure the statistical properties of those fluctuations, use those as initial conditions for simulations, and on the scales of galaxies or larger than galaxies, we can predict the basic properties of these fluctuations. And this is really mostly linear theory. The simulations go into the nonlinear regime, but where we understand them well, it's just gravity. Once feedback becomes important, things get interesting and hard. But on these larger scales, you run these simulations, look at the properties, now measure the power spectrum of the galaxies, compare that to observations, and this shows measurements of the fluctuations, the amplitude of the matter versus mass scale. And you can see where we are now is on these large scales, and this is the scale of a galaxy. So I'm not showing anything on galaxy scales or smaller. That's complicated, interesting, and much less well understood. But on the galaxy scale, the scale of the visible universe, our theory, which is the dash curve, does a very nice job, normalized to the measurements of the microwave background, of fitting observations of clustering of galaxies, large-scale structure, measurements of lensing. So in many ways, we have a very nice situation of a simple model fitting all of our observations.
Do you have a formula, or is this a simulation?
You can do this at this level. You can just do linear theory.
Dark matter included?
Dark matter included. So you must include dark matter, but you take these 5 parameters that fit the microwave background. You then do linear theory, and from about this scale up is all the linear regime. This is in the mildly nonlinear regime. You could actually do that analytically in fits that are compared to simulations.
Excuse me, David, again. I'm old enough to remember when your community didn't know what the cluster of galaxies were.
That's right.
Then our community discovered, there's more plasmas than. Okay, so I think you may have to rectify again your views. Don't you agree?
It is certainly likely that there are important things we don't understand. But I think what has been remarkable in the past 20 years is that as the data continues to improve, this same theory continues to fit the data. Now, it's a theory that has some strange things in it, right? It has the universe having dark matter and dark energy.
Now, this is a theory based on the initial. This is a theory based on your initial conditions of observation.
So you can.
So you describe a time t equals 0, and then put in the parameters and let it evolve, or what?
So you can describe the state very well at the time t equals 380,000 years.
Okay.
That's not 0 for us. We'll get back towards 0.
That's jargon. Okay, that's what.
So t equals 380,000, and you run it forward to today at t equals 13.75 billion. And you can compare it at many different times. Now, going back in time from 308,000 gets interesting. One of probably our best idea now on where to start is at the end of what we call inflation. That's a period of rapid, an accelerating phase where the growth rate, the size of the universe is accelerating larger and larger, growing exponentially. This period of inflation took place at t equals 10 to the minus 33 seconds, which isn't 0 either. It's very early. What was before that, I'll leave to Martin and his talk on the multiverse. He won't answer it, but he'll at least raise some of the questions. And one of the interesting things about this very early universe model, this inflation model, is it makes specific predictions for the statistical properties of the fluctuations. Those ideas were developed in the 80s. And with our observations with WMAP in 2003 and the follow-up observations with Planck, we seem to see something very consistent with it. So not to say that we understand what's going on, that we've learned a lot. We're left with some very big questions, and I'll just end my talk with them. We don't know what the dark matter is. We don't know why the universe is accelerating today. While we talk about this idea of inflation, we have not really embedded it deeply in our ideas of fundamental physics, making connections to how we unify theories, understanding questions like what was there before inflation, how do you tune inflation, does that model really make sense, are really open questions, and ones in which there's a need for a great deal of work both on the theoretical side and on the observational side. And observations, we hope to do things like detect gravitational waves from the early universes as steps beyond what we already have. So let me end that with a sense of where we are in cosmology. Thanks. But, a question?
Yeah, you have as a.
Could you use the microphone, please?
Oh, that's easy. Is it on?
Yes.
Okay. So you have your first bullet on what was the first bullet that just disappeared? Said that why is the universe accelerating, and that's an open question. So I presume that's not predicted by the model, and yet you seem to get today very well in the evolution.
It's put into the model by hand. It's one of those 5 parameters, if you like. We're putting in dark energy. We're putting in dark energy that's a vacuum energy associated with empty space.
So the question is what's the theory that causes dark energy?
That's right. So right now I can turn to my colleagues running computer simulations and say, put in 73% dark energy today and keep it constant, and that fits the observations.
So this standard model of cosmology is in the same state as the standard model of particles. It's got empirical constants put in, and then you can explain everything.
It has empirical constants put in, and like the standard model of particle physics, it has features in it that we don't understand well at all, right? Why, the origin of the different mass scales. Why is the energy scale of electromagnetism and the weak interaction so different from the energy scale of gravity? The energy scale of this dark energy, you'd think would be associated with quantum gravity, so it should have an energy scale set by the Planck scale. Yet it's, 10 to the minus 123 or something, I forget, times smaller. So it's obviously not the right unit to express it in when we're working in Planck units. we need a deeper theory connecting quantum mechanics and general relativity, connecting our ideas in particle physics to understand what's going on with the dark energy. We don't have that yet. On kind of the astronomical side, one of our goals is to be able to constrain the properties of the dark energy by seeing how it evolves in time and how it clusters. And a lot of observational work in cosmology is geared towards that.
So I guess Roger's next.
Charlie, Ellen, thank you very much for inviting me. I'm honored to be here and thoroughly enjoying your eclectic event and all the talks. I was asked to talk about something that was simple and short and easy to understand and, in presentation, but not understood in practice. And this is something that I think the last I will get across quite well. There's been a lot of history and politics so far, and this is my one contribution to this. Virginia, I believe, I hope will recognize it, not call me on this. I'll leave you to read it. Some of you may think that this is Charlie presenting to the NASA administrator. However, it is not. It is, of course, who discovered the Crab Nebula, and what I want to say follows on directly from by agreement with Ferd's talk this morning. So you're going to cast your mind back to Ferd's talk and the questions that he asked, and then I'm going to carry that story forward. Okay, so here is the Crab pulsar and its nebula, and to remind you, it looks like that. And it's a spinning magnetized neutron star. When Charlie and I first, and Martin and Virginia started think about that, it was 33 milliseconds, the period in two significant figures. Now it is 34. And that means it's slowing down, and that the loss of rotational energy, as Ferd said, goes into powering the nebula. Just one thing that he didn't have time to say is, and it's crucial to this business of shocks, and I will bring it out because Charlie will be interested in this, is there's an inner knot there that's half an arc second away from the pulsar that's studied with Hubble and adaptive optics. Highly polarized, strongly toroidal field, 60% polarization, and it's not very luminous. That, as Charlie will instantly see, is a very constraining observation for telling you what the sigma of the wind is and so on. So let me just leave that there. I won't go on to that. But what I do want to go on to is the gamma ray flares, which Ferd also talked about. And here you get gamma ray flashes in 400 MeV. These are 400 MeV gamma rays not seen anywhere else, and those are created as synchrotron radiation by 5 PeV electrons. Now, for the space physicists here, I better translate. A PeV is a rather large number of keV, and it's 10 to the 15 electron volts. And those are the electrons that have to be accelerated to explain the gamma rays that you see, and even particle physicists are impressed by that, because it's 1,000 times what they can do. So now, the key thing here about these observations is you get variations on time scale of hours from a region that is light years across. And nothing can travel faster than the speed of light, with the possible exception of a rumour, which is okay because it carries no information. So it tells you've got to get this large region, and a tiny bit of it has got to make a significant amount of power in a bursty sort of way. That's the puzzle. And it's not the only place where we see this happening. Here's the very first quasar that was discovered, 3C273. Here's the famous jet that comes out of it. It's powered not by a neutron star, but by a billion solar mass black hole, and you get gamma rays from this relativistic jet coming out here. In this case, Fermi sees 15 GeV gamma rays. Again, it's the same story. You get variation on timescales of half a day or so from a region that's 30 light years out. Okay? Another example, blazars. These are another type of active galactic nucleus. In this case, it was a slightly smaller spinning black hole. The gamma rays, this time, not GeV gamma rays, but TeV gamma rays. That's TeV is 1,000 GeV, and 1 to 10 TeV seen with atmospheric Cherenkov detectors. Rise times as short as 2 minutes reported. Some argument about how far out they come from, but probably not much less than a light day. Again, a lot of power produced all of a sudden from an extended region. Gamma ray bursts. I always think they should have been called quasars, just because it would have helped the occasion, but that never stuck. Here's one that was investigated by Fermi. They're believed, the majority of them, not all of them, there are different classes, but the majority of them are believed to be the birth of 10 solar mass black holes, spinning black holes inside a supernova explosion. Gamma rays are seen, that's a gamma ray burst, in this case a hyper-relativistic jet, much faster than the ones in the AGN. You see a gamma ray with Fermi, this is the largest one that's been seen, energy that's been seen, 100 GeV. Timescales as short as milliseconds, and in the flare, we're not quite sure, but coming from, again, a very large distance out. The same phenomenon, and these gamma ray bursts happen at a rate 1 per day. And then just finally, in the observational examples, I'm going to tell you about something that is highly uncertain, and its observational status is still controversial, and these are fast radio bursts which have been seen, and for completeness I'll call them phasars, although I can guarantee that won't stick. These are believed to be cosmologically distant, they're radio transients, they're timescales of milliseconds, and if they're real, which is indeed a matter of controversy, there will be roughly estimates of quite wild, but it's about 1 per minute over the whole sky. So that's pretty, and the most least implausible source of these are magnetars, but again it's the same phenomenon, something that has to be pretty big, making short timescale variation. So those are the observational stimulation, if you like, and if we ask what's common to these objects, then the prime movers are magnetized, spinning black holes and neutron stars. And so what you have is a little bit like what you saw from Margie this morning, was something that's spinning. It's basically a conductor, and it winds up unstable magnetic field with relativistic plasma, and it creates large amounts of toroidal field winding up like this. That's turning up. And so this is actually a simulation. This is the same sort, showing the similar phenomenon, analogous phenomenon to what Margie showed. This is actually a black hole in general relativistic MHD, done non-axisymmetrically, as she emphasized this morning was important. And you can see this hula hoop type activity there, this oscillation that's breaking the symmetry and so on. This is actually also a simulation. It just looks like a cartoon, but it really is it's a simulation. And for those of you who don't believe in simulations, you can perform the following analog experiment when you go to work in the morning, and you spend a lot of time just sort of untangling all of these cables that you've got in your backpack, and they get tangled up very, very, very fast. And so the contention is, as you heard this morning, that there's all this toroidal field is intrinsically unstable in a variety of ways, and it gets itself all tangled up. Okay, so let's move on. Now, this, the title I use is Magnetoluminescence, and this is perhaps a bit of an in-joke, but Charlie's erstwhile colleagues at UCLA in the physics department were famous for doing studies of a subject called sonoluminescence, and that is when you create bubbles and you have sound waves, and they collapse and they create high-energy radiation, X-rays and ultraviolet and all the rest of it, and it turned out to be a fascinating phenomenon physically and actually useful in some contexts. Now, what we have here, and I'm going to christen this magnetoluminescence, and I guarantee that name won't stick either, and this is basically what one has in the Crab Nebula and the quasars and all the rest of it is this toroidal field that's wound up like this, going unstable, and you know in these objects that's got to get dissipated. It's got to get converted into very high energy electrons which emit gamma rays and other good stuff for the gratification of observational astronomers. And it's done under highly relativistic conditions, so that's where it's really quite different from traditional space physics.
So you break the Frost-Sedin law with the relativistic effects?
In order to go unstable and dissipate the magnetic energy, you have to break the so-called, I assume you're speaking about fluid equation with relativistic...
No, not necessarily. Hold that, I know where you're going, Bruno, hold that thought, okay? So you've got to make the high energy electrons and positrons, it's going to be probably a pair plasma, and then go to gamma rays. And then in these sources, you've got a steady component and a flaring component. Most of the average power comes out in the steady component, but you get these bright, dramatic flares. And in order to do this, so again in the Crab, you've got to have region, about 5 to 10 light days across, convert all its energy, that's the minimum amount you need, in about half a day. So you've got to have...
We want to understand, yes.
Yeah, that's the puzzle, okay? Okay, you've got the puzzle. So the contention is you can't just do this in a piecemeal way. You've got to have giant volumetric particle acceleration going on under these conditions. And furthermore, to do this efficiently as you have to, you can't just have some cosmic pinball machine. The current has got to be carried by the emitting particles themselves. The resistivity is colliding with the vacuum and so on to create the gamma rays. Okay, so where this obviously leads is what about these knots and tangles? And this is where this is where the controversial part, I hope, will come in, and I hope I'm going to get some discussion going. I want to distinguish knots and tangles, and the nomenclature is a bit hard because Boy Scouts don't talk the same language as mathematicians, and the definitions are a little bit variable. But basically, we think we know what a knot is, something like that, and the mathematicians can tell us a lot about it, and you can, in this case, the trefoil, you can describe it by algebra. Actually, the mathematician first student, I've always amused me, his name is Alexander. And another Alexander is quite famous for the Gordian knot, which he did in a different way. But what I had only recently discovered, something I'd forgotten, was that in the legend of the Gordian knot by Alexander, when he sort of cut the thing, it was followed by a large electrical storm. Those were the classical education. So that's proof. So anyway, but the key thing here is that you need reconnection. You heard that this morning. Again, reconnection is an odd word, like the Re's in cosmology. It's the first time those field lines have ever been introduced in the social sense, so there should really be connection. But the reconnection is required to untie the knots like that, something like that. And that's a different process from untangling, which might be something like that, which you can do without changing the topology. So then, and if we try and classify the tangles, which are sort of slip knots and hitches and things like that, you can make a sudden transition to a lower energy state and get a volumetric particle acceleration if something like this is a good metaphor for how real electromagnetic fields behave. So the question is really... Oh, gone back. Okay, there we go. Oh, wait.
Don't try to tie knots when you've got a...
That's right, yeah.
In your hand.
Don't... Yeah, okay. So the real question then is, can you make is this sort of hairy rope model a fair representation of cosmic magnetic fields? And that, many observations that one makes in astronomy strongly suggest that. Others may think of magnetic fields as smoothly varying and not developing current sheets and all the rest of it. And that's the sort of puzzle that I throw down for the people here in the audience. And if you can argue that something like that actually does happen, then you have a rather efficient mechanism for volumetrically accelerating particles to the maximum energies available with the potential differences across these regions. Okay, so where are we going now? Okay, maybe I'll come back to that. So just to summarize very quickly, I think a new mechanism is needed to account for these quite generic dramatic flares. There's nothing wrong with traditional second-order Fermi, diffusive shock acceleration, all of that. That's all good stuff too. But these I think, are something different. They're associated with spinning magnetized compact objects, and they've got to dissipate this electromagnetic energy very rapidly. And perhaps the steady emission comes from the relativistic reconnection, which we heard discussed a little bit this morning. That's a natural way to do it. But this impulsive, bursty emission, maybe that comes from untangling flux tubes and the rest of it, and the details to be done. So a happy birthday, Charlie. Glad to be here, and look forward to hearing answers to all of these questions. Thank you.
Great, but can I first say how great it is to be here for Charlie's event. I first met him at a time he was working with Third on the Crab Nebula, and I've kept up with him and recently had very stimulating lectures from him when he's been on visits to Cambridge to tell us about climate change, environments, and other really difficult subjects where he is also a master. I'd also like to say it's good to be back in La Jolla. because I first came to La Jolla to see the Burbages. And I thought it would be nice to start off with this picture of B squared FH. This was taken actually at Willie Fowler's 60th birthday in Cambridge when he was given a model train. But I think it's important to remember that B squared FH is one of the great achievements of 20th century astrophysics, and it's great that a lot of it was done here. And I have warm memories of meeting them here. Well, I wanted to talk about two topics which are going to be, I think, relevant in the future, not the past, where we don't know very much yet: exoplanets and multiverses. David Gross at the ICTP Center says that he rates the liveliness of a subject by the inverse correlation with the average age of the participants in the workshops there. And by that criterion, he told me the most lively subject was exosolar planets. And I think that's understandable. It's a new subject, developing very fast, and it's going to continue to develop for at least the next 20 years. So just a few words about it. It's wonderful, really, to know that nearly all those stars we see in the sky are orbited by retinues of planets. And they've been found by very simple techniques, not seen directly in general, but inferred by their effects on their parent star, either by detecting the small wobble in the star's position due to the orbiting planet as the star and planet orbit around their center of mass, the barycenter. That's one way, and this requires detecting a Doppler shift of only a few meters per second. And here's an example of a very good circular orbit planet. This technique obviously gives you the mass and the period of the planets, but it can only be used for big planets, bigger than the Earth in general, because the Earth induces in the Sun a motion of only a few centimeters per second, and that's not enough to be detected by optical spectroscopy. But there is, of course, the other method, which has been able to detect planets no bigger than the Earth, orbiting stars like the Sun, and this is a simple method of transits, noting that when a planet moves across in front of a star, it'll dim the star slightly. If you look a long way away and see the Earth moving in front of the Sun, the dipping is about 1 part in 10 to the 4th. And one of the recent great space successes has been the Kepler spacecraft, and I think Bill Barucki, who worked for decades on this, deserves tremendous praise for what he did. And this telescope looked for 3.5 years at a patch of sky about 7 degrees across, measured the brightness of 150,000 stars in that field of view to a precision of 1 part in 100,000 over and over again, once or twice an hour, looking for these regular dips, and it found thousands of planets, many like the Earth. And I'd like to show some of the display, but it's a rather nice picture, which someone produced, which shows to scale the planets inferred by by Kepler. And, of course, special interest attaches to planets which are rather like the Earth, in the sense of being about the Earth's mass, and also at a distance from their parent star, such that water could exist. And the best quoted example, which was quoted a few months ago, is the top one here. The bottom shows our solar system, and the top shows a system orbiting a star half the mass of the Sun, and therefore a lot fainter. And this system has 5 planets, and the outermost of those 5 planets has a mass, so radius about 1.2 times the Earth's radius, and would be rather cold, but water could just exist. And that's one of the best candidates for an Earth-like planet. Now, of course, all these planets have been seen only indirectly by really seeing the star they're orbiting, and we'd like to actually image them directly. Let's suppose that aliens were looking at the solar system with a big telescope. Then they would see the Sun as an ordinary star. They see the Earth, as in Carl Sagan's phrase, a pale blue dot, very close in the sky to its star, our Sun, and much fainter. But if they had the angular resolution and the sensitivity to image the Earth and the Sun separately, far-flying extra searchlight, as it were, they could learn quite a bit. Because the shade of blue will be a bit different depending on whether the Pacific Ocean or the landmass of Asia was facing them. So they could learn that there were continents and oceans, the length of the day, etc., and something about the climate. And they could also, perhaps by analyzing the spectrum, learn something about the atmosphere and maybe that it was a biosphere. Well, we can't do that yet, but we'll be able to within 10 or 20 years. We'll be able to look at Earth-like planets around other stars and draw inferences like that. And I would plug, this is the proposed European big telescope. We're not very imaginative in name, so it's called the ELT, which stands for Extremely Large Telescope. And it's planned to have a mirror of 39 meters diameter, a mosaic of 800 pieces of glass. And of course, there are two slightly smaller telescopes being planned over here. But these telescopes should be able to detect Earth-like planets around nearby stars and separate out their spectra from the spectrum of the star and draw the sort of inferences which my imaginary aliens were drawing about the Earth. And of course, there are space projects. This is an old picture of the terrestrial planet finder, a NASA mission which was abandoned, but I'm glad to hear that there may be a revival of some kind of instrument like this to do this kind of project in space. Now, of course, what one really wants to know is there any life, any biosphere on these other planets? One may see some evidence for it in the spectrum of the planet. But of course, the other line of attack is to learn more about how life began on Earth. And remember, we don't know that. And to mention a local hero, Leslie Orgel here was one of the great pioneers of trying to understand the origin of life. And there's very serious new work being done by, for instance, Jack Szostak at Harvard and John Sutherland at Cambridge, new ideas on how life might have began. And that'll tell us whether it was something that was likely to happen anywhere or whether it was a rare accident. So simple life, we may learn whether it's there, we may learn how likely it is. Intelligent life, of course, all bets are off, but I think all of us think it's such an exciting topic that we should search for it by all possible techniques. Of course, some of us, and I get letters from people who know the answer already, and I get these letters from people who've been visited or been abducted and made corn circles. And I say, would these aliens really have made all this effort to come here and then met a well-known crank and gone away again? It doesn't seem very likely. And I also tell these people to write to each other and not to me. And, yeah. But there are lots of these people. I'm sure you get letters of this kind as well. Well, so much for planets around other stars, which I really think is going to be the most exciting topic for some time. Let me now turn to my other topic, things related to the Big Bang. Well, David has reminded us of the history of the Big Bang, and I'd like to just emphasize it's divided up into three stages. The first 10 to the minus 12 seconds is uncertain because the physics is more extreme than we can produce even with the LHC. The easy bit is between about 10 to the minus 12 seconds and about 100 million years. That's when it's all linear, we think we understand the physics. But then it gets complicated again because the nonlinear structures start forming. And we have this is just another picture like the one that Dave showed. Well, if we ask what are the areas that are going to be developed in cosmology, there are two kinds. Studying the later universe, where we want to understand the complexities, and this is what I'd call environmental cosmology. We want to understand why the universe looks like that. Dave indicated why it's not surprising that we end up with these galaxies, given what we know about the early universe. And let me show another picture which shows how a galaxy might form. So we are trying to understand how the first stars formed and the first sub-galaxies and the first galaxies, etc. And this is a subject rather like meteorology. It's very, very difficult. Vern Israel contrasted two kinds of science, mud wrestling and chess. And mud wrestling is this later part of the universe. But on the other hand, there's another set of problems in the early universe. Oh, I said in this picture, the blue is the dark matter, the red is the baryons that make the stars. And the other issue is about the very early universe, because important questions like why the numbers have the value we find, the dark energy, and how extensive is physical reality, these can't be answered unless we go right back to the beginning. And I want, if I can have 2 more minutes, to say something about a very important question, which is how big is the universe? How big is physical reality? Now, we know, I put this hazard sign here because it gets speculative. We know that there's a horizon around us set by the maximum distance light's been able to reach since the Big Bang. And the distant galaxies are near that. There's a shell around us. But that's got no more physical reality than the horizon around you if you're on a boat in the middle of the ocean. You don't think the ocean stops beyond your horizon, and we don't think that the universe stops beyond our horizon. It goes on. There are good reasons for thinking it goes on probably at least 1,000 times further. Those reasons are that if we look as far as we can in that direction and that direction, the difference is only 1 part in 10 to the 5th. And so if we're in a large finite structure, its gradient is very small. And it could go on much, much, much further, of course, so that there are combinatorial options all fulfilled and we have an avatar way out there. That's certainly possible. But that's not all, because this is just the aftermath of our Big Bang. And the other speculation is that our Big Bang is not the only one. Indeed, there are lots of different versions of the inflationary model, and they're different largely because the physics to put in at 10 to the 16 GeV is uncertain. But some of them, in particular those worked out by Andre Linde, have the consequence of what's called eternal inflation. You just get a whole lot of these Big Bangs. And this is a tenable view. Whether it's right or not will depend on what the physics at 10 to 16 EV turns out to be. And we don't yet know. But if we know the physics at 10 to 16 GeV and can test that physics in other ways, then this idea might gain credibility. But I think one of the challenges for the coming decades in cosmology is to decide which part of this decision tree is correct. First, how many Big Bangs are there? Is it just one, or are there many? If there are many, then are they all the same? Or, more interestingly, do they end up governed by different physical laws? Do they cool down differently so that some are sort of sterile and stillborn, others allow complexity to arise? And this leads to the idea that if there are many Big Bangs, we're not in a typical one, we're in a typical member of the subset which allows complexity to evolve. This is what's called anthropic selection. This is something which we may be faced with because there may be many Big Bangs, and many string theorists in particular think that there could be many, many possible vacuum states and many different physics. So I think we have to be open-minded about this. And some people take it seriously, others don't. And I'll just finish by quoting from what happened at a seminar at Stanford a few years ago, where some of us were asked how seriously we took the multiverse idea. And I was on the panel, and I said, well, on the scale, would you bet your goldfish or your dog or your life? I was nearly at the dog level. And then Andre Linde, who was on the panel, he said, well, he'd spent 25 years of his life developing this multiverse, and so he'd bet his life on it. And then later, when told about this, Steven Weinberg said he'd happily bet Martin Rees's dog and Andre Linde's life. So this is something which is now speculative. But if we think of what's happened in the last 50 years, 50 years ago, we didn't know whether it was a Big Bang or not. That was before Penzias and Wilson. Steady state theory was still in the game. And we've gone from that to being able to talk seriously about right back to 10 to the minus 9 seconds, maybe even right back to the time when an entire universe was squeezed to microscopic size. That's immense progress, so we can't be too pessimistic about settling these more fundamental questions in the next 50 years. Thank you very much. Question here.
Just a comment. I think measurements.
Yeah.
One potential way to make progress on this is measurements of the geometry of the universe. Right now, we know the geometry is close to flat.
Yes.
As we're seeing a small portion. But if it turned out that the universe was positively curved, for example,
yes,
that would imply that we don't live in one of these inflationary bubbles.
Absolutely. Yes.
And that there'd be one Big Bang.
Yes.
So it could, while these questions seem in many ways to be very speculative, there is a potential, I think, to make observations.
Indeed,
progress.
yes. And I think I'd also like to counter before someone makes the point that we're talking about things that can't be observed even in principle. And I'd like to say that's not too much of a problem, because even the most conservative astronomer believes that there are galaxies which are beyond our present horizon. And of course, if we lived in an Einstein-de Sitter universe, then they'd at least come within the horizon eventually. But now, if they're beyond the horizon today, they'll always remain so. So everyone believes in galaxies that are aftermath of our Big Bang, which are always unobservable. And so it's only a small step beyond that to talk about the aftermath of other Big Bangs. It's like sort of aversion therapy, where if you don't like spiders, you start off with a little spider a long way away and end up with tarantulas crawling all over you. And so I think you can be made to persuade that the idea of other Big Bangs is part of science. But of course, it'll only be taken seriously if it's a consequence of a theory that can be tested in other ways. And the hope has to be that at some stage there will be a unified theory which tells us the physics at 10 to 16 GeV, which is when inflation or something like it happens. And if that theory is vindicated by telling us about the hierarchy problem, massive neutrinos and things like that, then we will take its other predictions seriously. And I think only if that happens will we take this seriously. But I agree there are other ways in which we can get clues and eliminate options. Yes?
Can any of the two or three of you give us a current update status of the Planck measurements and the inflation arguments that are going on, and the kind of article that you have written, David? Does anybody want to volunteer, or would you rather pass?
Well, I'd like to make a remark, but then he will give the expert view. I think whatever the rights and wrongs are, the Harvard people made a big mistake hyping up their work so much. They should have published their paper, got it refereed, and then a version would have come out as it eventually did come out in Phys.Rev letters, and they had priority. And then we will see, when we have the better Planck data, to what extent their results have been contaminated by the foregrounds. What surprises me is they should have realized that there was more data coming from Planck and other data, and we will know by the end of the year whether this primordial component with the sort of twisting motions survives. But that's just my unexpert view, but David is the expert.
No, I mean, to give people who haven't followed this story some background, one of the very interesting predictions of the inflationary model
Yes.
is back at 10 to 16 GeV, gravitational waves are produced. And these gravitational waves would produce a distinctive pattern of polarization.
Mm-hmm. Mm-hmm.
The problem is that same pattern of polarization can also be produced by dust in our own galaxy. So what many of us have said for a long time is, in order to make a convincing case of this, you need to measure this at multiple frequencies. Very sensitive experiment done by a group led by John Kovacs at Harvard called BICEP that made the most sensitive map of the sky at a single frequency, basically. They have some higher frequency, a lower frequency measurement, a key measurement of single frequency. They saw the pattern that's consistent with gravitational waves, so made a really big deal about it on an unrefereed paper. But when a lot of us looked at it more closely, we found that the data was equally consistent with dust and with expectations for the dust in the region. And to make a claim of this importance, many of us feel that you really need to have a very convincing case of this. Fortunately, Planck is also making polarization measurements. And Planck is designed to measure things at 9 separate frequencies of temperature and 5 in polarization. So with its multiple frequencies, it can distinguish between galactic dust and a cosmological system. The Planck results are coming out in November. Mm-hmm. They have measurements in the same region as BICEP. So we will have both Planck measurements across the whole star and BICEP and Planck measurements in overlapping regions. I think with that, we'll know the nature of these fluctuations. I think my own bet is that they're likely going to be due, unfortunately, just to dust, because what we know about dust in that region is consistent with the signal we see.
Yes.
But we will know much more with the Planck data.
Yes.
There's an interesting sociology question of how they should have acted.
Yeah.
If this turns out to be real, but you couldn't prove it from their data alone, how should credit be distributed? But
Yeah.
the ultimate question really is,
Yes.
do we see gravitational waves?
Yes.
If we are to see them, it would tell us an enormous amount of
Yes.
personal.
And it is spectacular. I mean, the idea of inflation, it's true, it's more than 30 years old, but it is remarkable to talk with a straight face about a time when our present universe was squeezed down literally to that size. And when even more, when the Hubble radius was 1 billion times smaller than an atomic nucleus. So we're talking about a really extreme phenomenon, and that we can get any kind of predictions, like Gaussian fluctuations, out of this model is remarkable. And this does indicate that we've got quite a long way in the last 50 years. Yes, I could point you to Lucretius as well. So yeah, yes.
Copernicus in visually not geocentric cosmology.
Right.
Now people begin to discover this person, and you may be interested. I learned that he is buried in the same church where the Michelangelo built the statue of Moses by Michelangelo in Rome. And his tomb is represented by a crab, because the name in German was related crab. So this German
Yes.
was quite remarkable.
Okay. Yes.
He predicts, first of all, that the Earth was not the center of the
Yes.
universe, that there would be several universes.
Yes.
Yes, well, there's Grosser Tester and Bruno and all those people, of course, but they didn't know the difference between a solar system and a universe, of course, at that stage. Yes. Yeah.
I have a question as an ignoramus on this.
Yeah.
If there was only another trick microphone. If there was only one Big Bang, then, as you said, before that Big Bang, there wasn't any time or space because everything was enfolded. But you said that.
I didn't say that. I would have said we don't know.
But if there were only one Big Bang, you said that the universe exists beyond the outer horizon, the 13. But what would there be there in the sense that nothing could have got there in the time available? I mean, would it just be completely empty space?
No, it'd be just the same as now. You're mistakenly thinking that you can apply special relativity and the speed of light in this context. So it'd be just the same. It could go on forever. Indeed, the oldest cosmological model, the Einstein de Sitter, was infinite, and that had no contradiction. I think any theory predicts that there are galaxies beyond the domain we can now observe.
Yes, but not.
Yeah.
I just say,
sorry.
Not if there were only one Big Bang, the entire universe.
No, I mean, no. We could have a billion times more matter than we can see, all the aftermath of our Big Bang, all tracing back its origin to the same point, as it were. But of course, going back to the issue of before that, then the one thing we almost certainly will have to do when we get back to the very beginning is jettison common sense ideas of 3 dimensions of space and 1 dimension of time ticking away. As you know, one common idea is 5 or 6 extra dimensions coming into play on that small scale, and so the idea before and after may have to be revised. So the idea of a beginning of time, well, of course, one metaphor is to say it's like asking, can you go north from the North Pole? It may be a question like that, but we just don't know. But the point is that we need some new physics, obviously, and what's amazing is we can go back so far without some manifest contradiction, but clearly we've just pushed the barrier back to another stage where we face a new mystery which we couldn't even have posed before. Yeah.
Yeah,
Oh, yes, yes. Yeah.
One of the big things of the multiverse is that there'll be other universes and other physics laws.
Yes.
And the question is there any imaginable way of measuring this and confirming it experimentally?
No, as I said, all it could be is perhaps the consequence of a theory believed for other reasons, because string theorists, for instance, debate whether there's one vacuum state or many. If they get a good reason to believe that there are many, then you would expect that another Big Bang would lead to different physics. But quite apart from that, it's interesting to ask, what would the universe be like if you had different physics, different physical constants? And this is obviously a part of the program if one's going to have to take seriously anthropic selection. But even without that, I think it's fun to do it, because rather like, there's some historians who will ask, what would have happened if the Brits had fought better in 1776, or biologists ask what would have happened if the dinosaurs hadn't been wiped out. These counterfactual arguments are rather fun. They develop your intuition. And in the same way, it's, I think, helpful to ask the question, what would happen if you change the laws of nature? And there are lots of misperceptions about this. For instance, the gravitational constant. Some people say that has to be fine-tuned. It doesn't have to be. It just has to be very weak. The important thing is that there's one large number in physics which reflects the ratio of the electrical and gravitational forces between atoms. And it's for that reason that objects have to be very big before they're crossed by gravity. If you imagine building up sugar lumps, people, asteroids, gravity has no effect. Planets, it makes them round. Jupiter, it starts to crush it. Now, if you made gravity 10 times stronger, then you'd still get the same thing, but gravity would come in at a mass 30 times lower. So in order to have many, many powers of 10 between the microworld and the cosmos, you need one large number, which reflects the weakness of gravity. But you could have an even better universe if gravity was 10 times weaker, because you then have stars lasting 10 times as long, and weighing 30 times as much, and planets could get much bigger before we were crushed. So there's nothing optimum about that, but there is some tuning, obviously in the so-called dark energy, because if that was much stronger, then it would have made everything accelerate away from each other before galaxies could form. And also there's a more complicated tuning between the nuclear and the electromagnetic forces, because B squared FH only got the periodic table because the most tightly bound nucleus is iron, and you can get nuclear fusion, etc. But if you tweak those ratios, then you get a sterile universe. So it's interesting to ask what the constraints are. They're weak on gravity, and very strong on the dark energy, and fairly strong on the ratio of the nuclear and electromagnetic forces. Thanks. Thank you. I think we've got to move on now. Thank you very much.
About 1% of the stellar mass in our galaxy is in the form of superfluid neutrons or superconducting protons inside of neutron stars. And that in itself might be a sufficient reason for studying it in more detail than is presently available, but it is not a particularly prominent part of astrophysics. And what I'm going to talk to you about does not involve really any consensus about what's going on. And even Charlie has not yet made a significant contribution to this particular subfield. Okay. A neutron star is a giant nucleus. And ordinarily, we know a lot about nuclei, and this should be enough to say we know in detail what's going on. But we don't have available nuclei in the laboratory whose atomic number goes beyond 300. If we could increase that number to about 10 to the 4 or 10 to the 5, we would have in a nucleus all the properties we're trying to explore in a neutron star. But unfortunately, gravity is the only way to keep something together which gets heavier than that, and even that doesn't work until the mass of the, quote, nucleus reaches something like the mass of the sun. Now, what I'm going to do is remind you of some of the properties that a star would have if its central part was mostly superfluid neutrons and superconducting protons, and then suggest a narrative of ways in which that could determine enough of the evolution of such a neutron star so that we might understand things that would otherwise not be easily understood. And in particular, I'll choose how do we manage to give birth in our galaxy to things called millisecond pulsars, which are much less magnetized by several orders of magnitude than most pulsars, and whose angular rotation velocity is bigger by a similar factor of order 1,000 than that of most pulsars. First, we start out with a star filled just with neutrons for a moment. It's got a crust about 1 kilometer thick. If this was normal matter and you were rotating it and waited for all the transits to die down, it wouldn't make much difference whether the star was a liquid or a solid. It would be a star in which everything was rotating with the same angular velocity. But the case of a neutron star is different. It rotates by establishing an array of quantized vortex lines. The physics of these is very well understood. The number of vortex lines per unit area depends on the mass of the neutron, the angular velocity, Planck's constant, and so on. It's about 10 to the 4th over the period in seconds. They're about 10 to the minus 2 centimeters apart. If you looked at a rotating bucket of liquid supernova, neutral supernova, it would make an array of vortex lines, and you can sort of make them out with a magnifying glass. You'll note that it does not depend on the interaction between neutrons. It does not depend on anything other than fundamental constants and the mass of the neutron. So in the laboratory, I could mimic this in principle by using, instead of neutrons, helium-3. The density doesn't make any difference, just the mass of the particles. One understands this particular problem very well. What the structure should be for the rotation of, let's say, a sphere of superfluid neutrons. The superconducting protons are a simple approximation, very much like a perfect diamagnet. But if you've already got magnetic field in there, it's generally unable to expel that magnetic field in anything even resembling the age of the universe. And instead, the magnetic field probably organizes itself. I say probably, we know it organizes itself. It's a question of, has various ways of making that organization into regions in which the magnetic field is essentially zero, and other regions in which we have miniature solenoids, the field being about 10 to the 15th Gauss. The magnetic field inside of a typical neutron star might be 10 to the 13th or 10 to the 14th. So the magnetic field in these miniature solenoids is very large compared to the average magnetic field in the core. And so this is the structure of the magnetic field in the neutron star, proton superconductor, and we saw also what the structure is for the rotational structure for the superfluid neutrons. Both exist in a neutron star. If the neutron star is spinning down, most of it is neutrons. And the only way in which it can spin down is by having a smaller density per unit area of neutron vortex lines, because the omega is proportional to that number. So the only way in which the neutron star can spin down is if the vortex array expands. The vortices move out. It's a vortex array. The vortices cannot end except on the boundary, or in the case of a turbulent superfluid, they can form loops, but they don't have beginnings and ends inside the superfluid. So the neutron vortices begin to move outward. But in order for them to move outward, they have to find some way of getting through this extremely dense array of proton superconducting solenoids, which are just referred to as flux tubes. When they meet a flux tube, there's an extremely strong interaction between them. We know there must be an extremely strong interaction between them because the neutron-proton force is very velocity dependent, and you have in the solenoid, which is the flux tube, protons which are acting as if they're moving around in circular motion, as they would if they were the charged particles giving the current in a solenoid. And you have a rotational structure for the neutron superfluid around the vortex lines. And so when the neutron vortex line and proton flux tube get on top of each other, the potential of interaction is different than when they're not on top of each other. It doesn't make any difference for the story I'm going to be telling you, whether that's an attractive interaction or repulsive interaction. It is strong, it can be estimated, and there's no question but that if you slowly try to move a neutron vortex line through a flux tube, it's going to not enter the flux tube and just start to push on the flux tube, or it will enter the flux tube and not let go. But in either case, the neutron vortex line is going to be attached to flux tube. That means that when the star begins to spin down, we would have a problem such as in the lower right-hand corner here. We have a crust. The crust of the star in some ways resembles normal matter, except that its density at the interface between the core of the neutron star and what's above it has a density of about 10 to the 14th grams per cc. The matter in between the nuclei is filled with superfluid neutrons, which gradually dies out, and by the time you get up to the surface, you're down to somewhat like normal densities, which might in many cases still mean 1 million grams per cc. The neutron vortex line is moving, in this case, to the left. It interacts with, and this is just a cartoon, the flux tubes. It pulls on them. The flux tubes, however, are anchored in the crust because the crust is an extremely good electrical conductor, and extremely good normal electrical conductors anchor magnetic field. And so it's going to have a problem of pulling on the crust, and the crust doesn't want to let go. If you wait long enough, these crustal currents will die out, and it will let go and allow the flux tubes to melt. If not, you have to worry about the fact, will the pull on the crust be strong enough to overcome the shear strength of the crust? To do that, you have to understand where are the dislocations in this peculiar crust. How easy is it to move them? There are lots of physics problems in trying to make this estimate. Unless you try to make this motion very slow, because if the motion is slow enough, the eddy currents pinning the flux tubes to the crust die out, and you move the crust as if it was an insulator. All of those things can be handled to some extent, but probably not with much confidence, and many of them are extremely sensitive to the temperature. If they're extremely sensitive to the temperature, you have to know what the temperature is of the neutron star over there. The temperature depends a little bit on the prehistory leading up to that. The prehistory depends very sensitively on the mass, because the prehistory for the temperature depends on its ability to emit neutrinos, because it's neutrino emission that begins to cool it. That in turn depends very sensitively on the density structure deep in the core, allowed for neutrons and protons, which are interacting to give rise to neutrinos. And one doesn't really know how to make a reliable estimate of that at present. Everything I said up to now, I think, is not really in dispute. I'm going to look at a particular problem now, and it's going to be a narrative which would, I think, not be something which is opposed or applauded. It's just not been considered. Before I go on, let me say a word about narratives. I'm going to give you an astrophysics narrative. Our colleagues in the liberal arts are very used to narratives, and they divide them into two kinds. There are non-fictional narratives, a history, an essay, a documentary. These are all non-fictional. There are fictional narratives, a novel, a play, a television series. Without question, the fictional narratives have a better audience, are more applauded, and last longer. Okay. So that judgment may or may not be applicable to what I'm going to be saying, but you should keep it in mind. Here's an example of what would be expected to happen to the magnetic field of a neutron star if you spun it down extremely slowly, or, in the example given here, you spun it up extremely slowly. We start out on the left with a star in which this particular flux tube is one which starts in the upper spin hemisphere, and its north pole is indicated, and its south pole is in the lower spin hemisphere. The vortex lines begin to move inward. There's no other way you can spin up the neutron star. They drag the flux tubes with them if you do this slowly enough so that the crust can be just thought of as an insulated, not pinning anything. And you will end up with an aligned neutron, north pole, south pole, on the spin axis. So you would align, in this case, with a magnetic dipole moment essentially coincident with the spin axis. If, on the other hand, the neutron pole, south pole, there is the flux tube connecting them, are as in the bottom half of this diagram. This is one in which the flux out from the upper spin hemisphere returns to the star in the upper spin hemisphere. The same thing might be true in the lower spin hemisphere. And for ease of looking, I'm just drawing part of the picture. In this case, if you spun up that star, the N and the S get closer together, and you will end up with a dipole moment, which is orthogonal to the spin axis, which is placed at the interface between the crust and the core where the proton superconducting fluid ceased to exist as a superconductor. And you'll end up with a smaller dipole moment, not because anything decayed, but because the north and south poles got closer together. The neutron vortex line acts like a prison bars, pushing it together. They also keep them from reconnecting, keeps them at a well-specified distance. And I know what that distance is if I know the distance between vortex lines, and I know what the distance is between vortex lines if I know the spin angular velocity of the neutron star. A non-negligible fraction of neutron stars are in binaries. Here's a neutron star. That's a little dot on the left, which is too small to see if I made it to scale. And there's a companion star. There's a dot in the middle, which is the center of gravity between them. This is a co-rotating frame, and these continuous lines represent possible orbits of particles. Orbits around the star, the red star, go more or less circularly around it. Orbits around the neutron star, gravitationally bound to it, go around it. There are special orbits which couldn't quite make up their mind which one they go to. And for the experts here, this is just, of course, the Roche lobe. That particular combination can live for billions of years. So we can wait until some evolution occurs in that system. Either the two stars might get closer together just because of gravitational radiation, because we have several billion years to wait for this to happen, in the sense that these may have been made early in the history of our galaxy. Or the star on the right may finish burning hydrogen, may start to burn helium, and may start to grow as a red giant star. Many things could expand its physical size. It could begin to overflow its Roche lobe and begin to feed an accretion disk around the neutron star. If it feeds an accretion disk around the neutron star, and the neutron star is of the sort in which the flux from the northern spin hemisphere returns to the star in that same hemisphere, more or less a generalization of what you see in a sunspot duo. Then, the inner edge of the accretion disk is spinning around rather rapidly, much more rapidly than the outer edge of the neutron star, and it could be much more rapidly than the normal state of the pulsar we started out with. It will begin to spin up the star. But as it spins up the star, the dipole moment of that star gets smaller. If the dipole moment gets smaller, it can spin up the star more, because the inner edge of the accretion disk gets in closer to the star. And the lower diagram, if we started out with a dot on the right, that's a typical dipole magnetic field strength, which means averaging the surface field of the magnetized neutron star. It starts to move along that series of arrows. It spins up the star a little bit. The star's dipole moment gets smaller. And if you started out with normal old pulsar parameters, you would move along that dotted line, and you'd start out from a period of several seconds, and you can end up with a period of a millisecond. So what would happen in this case is that you would make a millisecond pulsar. It became a millisecond pulsar because it was spinning up and because of the fact that its dipole moment was getting smaller. So a millisecond pulsar should also be made with magnetic fields of several times 10 to 10 to the 8th Gauss. And that's where you find millisecond pulsars. And then the big question is, can you test this out in any other way than saying, well, that's a possible narrative of how that could occur? The top picture is a slice of the neutron star through its spin axis. There's that little dipole moment drawn in that plane. The open magnetic field line bundle goes off to the right, and then it comes in to the left. And I've neglected various things, such as the diamagnetism of the core and so on, which could be included in such a diagram. Of course, what you would expect to see in such a case is a radio pulse, if there would be one, coming to the right, and then as the star rotates through half a period, you'd see one from what is on this diagram, the left direction. So you should see two radio pulses separated by 180 degrees. And indeed you do, but there are lots of ways of getting that, because I needn't have the dipole moment up there. It could be anywhere on the spin axis, and indeed it could be anywhere on the star as long as it's reasonably perpendicular to the star. However, where the radio pulse goes through the surface of the star is what's normally called the polar cap of the star. Along that magnetic field line is where accelerators which will exist, which make the electrons and positrons, which we're all, I think, familiar with in the magnetosphere of a neutron star. A great deal of energy flows back and heats the polar cap. So you'll heat the polar cap on the right, and you'll heat the polar cap on the left. If that geometry is the right geometry, those two polar caps should be separated by 180 degrees in phase also as the star rotates. But if that dipole moment is removed from the spin axis, that would no longer be the case, where they penetrate through the surface of the star. What you see in this particular kind of star, and here's an example of it, is an X-ray intensity as a function of phase, which is, for that star, period 5 milliseconds, magnetic dipole field, which just means the strength of the dipole moment. You say I have 2 more minutes? Can't hear it.
You're already over 10.
I'm sorry. I will rush through, and I will not. I'll do only one other slide after this. One sees from the heated X-rays, and these have a quasi-thermal spectrum, so they seem to be heated polar cap, the expected 2 pulses. One sees, if you say, and that's the only arbitrary parameter in the problem, if you're looking at this from some angle, in that case it's the angle C, which is 60 degrees, you would see the pattern that I've drawn up on top, which more or less duplicates that. Unfortunately, this is counts per bin and is normalized in a different way. So what I'm saying is that it does give the 2 essential features of what you see in X-rays. Last remark, if you look at that same picture, you will note that looking at that, if that's 30 degrees, which is what it would be roughly, and looking up at that, you barely graze that pattern, so that the effective black body radiating area would be very small. And indeed, the black body area in these examples is about 1% of what you would have expected if this was a central dipole. Last one. This is not an arbitrary case chosen because it fits the data. This is what you see if you look at the 6th brightest millisecond pulsars as of 2009. And you'll see in the first 4 cases, the upper curve is the X-ray pattern, the lower curves are the radio pattern, and it indeed is true that the separation between those pulses is, as expected, very close to 180 degrees. It's independent of, the separation is independent actually of what the oblique angle is with which you are looking at these, which is something which is variable. It's certainly also the case that you don't get such easy agreement for everything. If you look at the normal pulsar population and asked how often do you see in the radio pulse 2 pulses roughly 180 degrees apart, plus or minus 40 degrees, let's say, whose amplitudes are within an order of magnitude of each other, it's about 1 out of 100. Whereas here, it's of order of magnitude at least 50% for the millisecond pulsars. So it's a narrative which is not necessarily unique, but is certainly alive. The more interesting question is what now happens when you apply the same way of thinking to spinning down neutron stars. And the cases are interesting, they're analyzable, and they will be available on the 85th birthday of Charlie.